Hi everyone. By the end of this video, you should be able to sketch a polynomial graph by figuring out what the zeros are and then determining what's called end behavior, which will be new. So this should look somewhat familiar. We have a polynomial in factored form. We studied quadratics, we studied polynomials. What we're going to do is just study polynomials of higher degree. So notice this one has 3 x's instead of quadratics, which would have a 2. Okay, so with that said, how do I find zeros? Well, zeros are where the graph crosses the x-axis, which means the y value is 0. So h of x is kind of like saying y, so we want our y to be 0, and then we have that equals this. And then we can use the zero product property to solve for the zeros, which essentially says if I'm multiplying these things and they equal 0, then either this needs to be 0, or this needs to be 0, or this needs to be 0, or some combination. So I would have either negative 5x equals 0, x minus 2 equals 0, or 2x plus 1 equals 0. And you can go ahead and solve those and figure out the zeros. So this one would give me x is 0. Here I would get x is 2. Here I would get x is negative 1/2. So we can already do that without much new learning. We can plot the zeros of a polynomial, even if it's not a quadratic. So here's where x is 0 and y is 0. Here is where x is 2 and y is 0. Actually, maybe I should make this a little bit wider. Here is where x is 2 and y is 0. And here is where x is negative 1/2. Okay, so I know my polynomial would have to graph or have to cross through these 3 points. Now, just knowing the zeros is not enough to sketch a graph, because I could sketch a ton of graphs that go through these points. I mean, it could look like this. It could look like this. I mean, there's a million different things it could look like. So we want to gather a little bit more information. And that comes from identifying some of the stuff you see on the side here. So first and foremost, our zeros are x equals 0, negative 1/2, and 2. Okay, what else can we graph? With what you know, you should be able to easily graph the y-intercept. And I've helped you out a little bit here by giving you this polynomial in factored form and also standard form. So I got standard form by just kind of multiplying all that out. So if I want to find, let's say, the y-intercept, I can plug in 0 for y and 0 for x, and I'll get my y-intercept. And in this case, if you do that, you'll get 0 equals 0, and that's because the y-intercept is actually the origin, because one of our x-intercepts is the origin. So we already know it's going to cross. But oftentimes you'll need to find the y-intercept that's not at the origin, and that's why I had you identify the constant term. Because if you have a polynomial such as like 2x squared minus 3, and you want to find the y-intercept, you would plug in 0 for x, and then you would get y equals negative 3. So the constant term usually tells you what the y-intercept is, as long as it's in standard form. So in this case, there's no constant. Okay, just a reminder, a constant is a term without a variable. Anywho, everything I've said over here should be a review. Let's talk about some new stuff. Okay, so we know our y-intercept, our x-intercept. I've asked you these other terms, so let's talk about that, and we'll talk about why you need to know that. So first of all, leading term. A term is one of the members of the polynomial separated by addition or subtraction. So these are all terms. And the leading term is the term with the highest degree. Or when I say highest degree, I'm talking about the highest exponent. Okay. And the reason I say leading term is because if it's written in standard form, it always comes first. But these won't always be in order. I could write this as 10x, 15x squared plus 10x minus 10x to the third. And this minus 10x to the third is still the leading term because it's not written in the correct order. So don't always look for the one that comes first. Look for the one that is the highest exponent. So in this case, our leading term is negative 10x to the third. Then our leading coefficient is the coefficient on the leading term, which would be negative 10. Okay, the degree is talking about the degree of the whole polynomial. It's the highest exponent, which would be on the leading term. Okay, which in this case, the highest exponent is a 3. So the degree is 3, which makes this a cubic graph. So constant would be something like y equals 2. Linear is like y equals mx plus b. Quadratic, we know what that looks like. Cubic looks like this, it's cube. Quartic is a 4th degree, so like y equals x to the 4th, just so you know. some vocabulary there. Okay, we're talking about sketching polynomials, so why do I need to know this? That's a very important question to answer. So let's take a look at this for a second. So say you have some polynomial. So in this case, we have like ax to the n equals y, where a and n can be any different values. Okay, so n is the exponent and a is a coefficient. So if this was like 1x to the first, that's just y equals x, that's why it's a line. Or if I make n 2, it's a parabola because I'd have 1x to the second. Okay, or if I have a third degree, it's going to look like this, cubic. Fourth degree is quartic. Fifth degree, sixth degree, oops, seventh, why do you keep coming up? 8th, 9th, 10th, 11th, 12th, 13th, so on and so forth. You should start to see a pattern with what these graphs are going to look like. And this link's on your note sheet for you to kind of take a look at. Now, that's if I change the exponent as n. Now, let's say I make n the 4. What does this a value do to it? So we should kind of already know from transformations that if it's positive, it's going to be facing up. If it's negative, it's going to be facing down, right? And then the larger the number, it's getting vertically stretched because the y values are getting bigger. Okay, now what if it looks like, instead of a fourth degree, what if we have an odd degree, like fifth? So then what happens, positive or negative? Okay, so really what's happening is it's reflecting over the x-axis, which I hope we know from transformations. Okay, so what is the point of discussing this? We're trying to sketch some graphs. And the reason we're discussing this is because by looking at those two numbers, so first of all, the exponent, let me go back to that. So the exponent here and the coefficient, we can determine what the graph structure is going to look like. Specifically, what is happening at the ends of the graph. When I say ends, I mean like here, oops, and like up here, those are the ends. Or, you know, if I make this a fourth degree, the ends are up here and up here. So with that said, let's take a look at our polynomial. And specifically, we're going to want to look in standard form to figure more out about what this graph looks like. So again, our graph is a cubic. And our leading coefficient is negative 10. So this negative 10 is going to reflect it over the x-axis, okay, which we know from transformations, right? So whenever that coefficient here was a negative, it reflects it over the x-axis. And then further, the x to the third, what does x to the third do? Let's go back to this. So if it's x to the third versus x to the fourth, what's going to happen is that the ends are going to go in opposite directions, which is similar for if you go to x to the fifth, or x to the seventh, or x to the ninth. Okay, the ends are going to go the opposite way. But if it's an even exponent, like to the fourth, or like a parabola squared, or 6, the ends are going to go in the same direction. So either both going up or both facing down. And again, this is called end behavior. So just by looking at that leading term, we can figure out what the ends of this graph are going to look like. So we know that the graph is going to look like a cubic, which would have ends going in opposite ways, except because it's a negative lead coefficient, it's going to reflect over the x-axis. So instead of, looking like the standard cubic, this one's going to come down, and this one's going to go, up. So with that extra piece of information, we can get a little bit more of an idea of what this looks like. So it's got to cross through those zeros, and it's got to have these ends. Now, obviously, I don't know exactly what's happening like around here or here, or whatever it means, but you can always plug in points to figure out a little bit further what it looks like. So maybe I could plug in like -1/4, and then I know like how low it goes here. I'm not going to do that for now because we're just trying to sketch a graph. What I do want to do is kind of summarize what we've just learned about end behavior. Okay, so there's a couple different ways you can describe this. First, you can describe the exponent. So if it's odd, the ends are going to be going in the opposite ways, versus if even, they're going to go the same way. And if the leading coefficient is positive, it's going to be like the regular version, so it's going to be facing like up, up. Or if it's odd, it'd be facing down, then up, if you read it like a book. Okay, as soon as you make the coefficient negative, it's going to reflect over the x-axis. Now we're going to formalize this if you flip on to the next page here. So to determine the end behavior graph, you want to look at the leading coefficient, because that'll tell you if it's positive or negative, and the degree of the polynomial. So if it's a parabola, it's going to look different than a cubic function, so on and so forth. And I always compare it to a parabola because that's something we should be very familiar with. So all even degrees will kind of look like this until they reflect, then they'll look like this. And then all odd degrees will kind of look like this, but then when they reflect, they're going to kind of look like this. So I only drew the pictures. You might want to write a summary of that on your own. I'm going to leave the bottom part for us to fill out together in class, and we'll kind of formalize this together again, but come with your own way of explaining how you determine end behavior by looking at the leading coefficient and the degree. Have a great rest of your night.